We have only 7 presentations, therefore the next one is the last one by Leslie Ann Ray. Please, thank you.
Thank you for the introduction. My name is Leslie Ann Ray, and I've come here today from Cranfield University in the UK. And I'm here to talk to you about the effect that substrate geometry and coating DFT or dry film thickness has on the cracking resistance of polymer protective coatings. This study was a joint venture between Cranfield University and AXA Nobel UK. So throughout the presentation, I'm going to take you through a little bit of the research background into what water ballast tanks are, the environment that they are subjected to, and also the coatings that are applied to protect the surfaces. I'll then take you through a little bit of the experimental testing that was carried out along with the results, and the finite element modelling that was completed alongside it, and finally some conclusions. So just some of the background. So crude oil carriers are used to transport heavy loads of oil across very large distances. And in order to compensate for varying cargo loads, it is vital for the ship's design to incorporate a water ballast tank system. So this system can be filled and emptied of seawater when needed in order to increase or reduce buoyancy within the ship. However, due to the highly saline wet environment, they are particularly susceptible to corrosion failure. And as we saw in the previous image, these water ballast tanks are embedded well within the ship's hull, so any repairs are going to be very expensive and potentially dangerous, and severe corrosion can result in the scrapping of an entire tanker. So the water ballast tank coatings are applied to the inner surfaces of the tank as part of the manufacturing process. During this process, the coatings will be subjected to extreme variations in temperature, either daily or seasonally, depending on the country of manufacture. Once the ship is then in service, the internal walls will be subjected to physical movement as the ship crosses choppy waters. Deabsorption and absorption of moisture will also result in coating shrinkage and swelling. And finally, there is a thermal fatigue cycle happening due to the crude oil, which is transported at approximately 60 degrees C, and seawater at less than 10 degrees C that is pumped in for ballast. And it is this temperature differential that my research is focusing on. So this is just an image of a water ballast tank that has succumbed to severe corrosion. And it has been observed in service that the worst cracking failure, and therefore corrosion, occurs within the corners and the welded areas of the stiffeners and around areas of complex geometry. So the purpose of my PhD study is to develop an understanding of cracking behaviour, including the process behind crack initiation and fatigue crack growth, and also to develop models capable of predicting fatigue endurance and the service life of water ballast tank coatings. This project in particular is focusing on understanding the effects of local coating thickness and substrate geometry on thermal fatigue lives. So in order to do that, a specific highly filled epoxy coating was chosen. Its mechanical and thermal properties were determined. It was then subjected to thermal fatigue cycles. And finally, finite element modelling techniques were employed in order to understand the strain fields that would develop within the coating. So just a little bit about the material characterization. So I was able to characterize the material's mechanical and thermal properties using free film standalone pate samples. So the modulus and strain to failure were identified using a tensile test to failure, fracture toughness using a double-edged notch tensile specimen, and coefficient of thermal expansion using thermomechanical analyzer methods. So the first thing to note is that the material is much more ductile than the steel substrate of which it is to be applied. And you can also see that as the temperature is reduced from 60 to -10, that the material becomes much more brittle and the strain to failure of the material is greatly reduced. We should also note that the strain to failure and the toughness properties of the material are significantly lower than that of the steel substrate. And finally, the coefficient of thermal expansion of the coating is 5 times greater than that of the steel substrate. which leads us into why strain generation occurs. So when the coating is applied to the substrate, it will begin to cure. This cure process will result in solvent evaporation and coating shrinkage. This generates tensile strains within the coating. As the temperature is then reduced from 60 to minus 10 degrees C or less than 10 degrees C, the substrate and the coating will both begin to contract. But as the coating has a much higher expansion coefficient than the substrate, it will contract at a much greater rate, resulting in further tensile strains being generated. So just a little bit about the thermal fatigue testing that's been carried out. As we saw in the previous image with all of the nasty corrosion on it, the worst failure is happening in these welded T-section areas. Therefore, a welded T-section of structural steel was chosen to be the substrate. In order to understand the effect of substrate geometry, one side of each T-section had its welds milled to provide a constant 2 millimeter radius along each weld length, while the other side was left as welded. So this gives us two conditions, a milled and a non-milled surface. And then also, as we saw earlier, the water ballast tanks are embedded very deep within the ship's hull. So this makes application far from ideal for the workers. Even under laboratory conditions, the dry film thickness of the coating can be up to 60% larger than the intended thickness. Therefore, two thickness sizes were chosen, 600 microns and 300 microns. So once the steel was welded and milled, it was grit blasted and spray coated. 5 samples were spray coated with a 600 micron dry film thickness, and 2 samples were spray coated with a 300 micron dry film thickness. All of the samples were then placed in an environmental cabinet and subjected to the following thermal profile. This is a dry cycling profile that lasts 5 hours between 60 and minus 10 degrees C, with 40-minute dwells at 23 degrees C, 60 degrees C, and minus 10 degrees C. So this is to simulate time when there is nothing in the container, when the crude oil is being transported, and when the seawater is being transported. So in order to understand what levels of thermal strain might be happening within the coating, this bimaterial strip method based on an ASTM standard was introduced. So this involves a coating applied to a thin shim, which was placed within the chamber along with the T-sections. As the coating contracts, the shim will deflect, and this deflection from linearity can be measured and translated into a thermal strain. So all of the coatings after application were given 7 days at room temperature to cure, followed by 48 hours of curing at 100 degrees C. And this was to try and replicate the in-service conditions that are achieved. So after cure, it was noted that a strain of about 0.2% existed within the coating. As the coating was heated from 23 to 60 degrees, the coating would expand, the shim would straighten, and strains would tend towards zero. As the coating was then cooled from 60 to minus 10 degrees C, and the coating began to contract, we would see an increase in thermal strain, with the largest strains being at minus 10 degrees C, which is, of course, when the material has got its lowest strain to failure. Of course, this just tells us what strain levels you might see on a flat surface of a coating applied to a steel substrate. So in order to understand what local strains might develop within the profile of the T-section, finite element modeling was employed. So this is a 2D plane strain analysis with a 2 millimeter substrate radius and a 300 micron coating applied to the substrate. The coating properties that were displayed earlier that were identified were input into the model, and a thermal load from 60 to minus 10 was applied with assumed zero strain at 60. So the image shows the strains or the stresses within the coating at minus 10 degrees C. So we can see very clearly that we're getting very high stress concentrations within the weld fillet area, and that the highest stresses will present at the surface of the coating. So these values can then be translated into thermal strains for comparison. and a series of models were carried out in order to investigate the effect of coating thickness and weld fillet radius. So sectioning of the actual T samples, an analysis of those, showed that in each sample there could be a thickness between 300 microns and 1,000 microns present within each sample. It also showed that on the non-milled weld there could be a weld fillet radii from 0.5 to 3 millimeters. So each of the individual models produced the following results for thermal strain at -10. It is very clear to see that as coating thickness is increased, there will be an increase in thermal strain within the weld fillet region, and a reduction in weld fillet radius size will result in further increases of thermal strains. So the condition that will produce the highest level of strains is a thick coating applied to a very small weld fillet radius. But also on the flat plate area, there was no change in internal strain, so it is completely independent of dry film thickness. So this is just some of the results from the thermal fatigue testing. So samples were removed at regular intervals and a handheld microscope used to investigate cracking behaviour. Images of the cracks were taken in order to measure crack length and determine crack growth rates. It was identified that cracks will initiate along the weld fillet area and will channel parallel to the weld length. So if we compare the cycles to first 1 millimeter crack identified for our 4 conditions, the conditions being 600 or 300 microns applied to milled or non-milled welds, and we introduce the thermal strains investigated using the finite element, we start to see a trend on how the local strain will affect the cycles to first millimeter crack. So the 600 non-milled weld condition will have a huge possible strain range because its coating thickness could be anything between 600 and 1,000 microns, and its weld fillet radii anything between 0.5 and 3 millimeters. But if we apply 300 microns onto a non-milled weld, this range reduces, and then the range is reduced even further as we apply the coatings to welds that have a constant 2 millimeter radius. So we can just see this trend appearing, that you've got very, very few cycles to first millimeter crack for all of the thick samples applied to an uneven substrate. So just in conclusion, strain concentrations will develop in the weld fillet region of a coated T-section, and local strain levels are very strongly dependent on the coating thickness and the substrate fillet geometry. Thicker coatings applied to smaller weld radii will experience greater maximum principal strains, and thermal fatigue lives of welded T-sections are strongly dependent on the local strain values at -10. So greater coating thickness applied to a reduced radius size will result in significantly fewer thermal cycles to first crack identified. I'd just like to acknowledge both AkzoNobel and Cranfield University for their support in this project, and also the Institute of Mechanical Engineers for financial funding. Thank you.